going to talk about the chi-square goodness of fit test. So first, we're going to start with a big overview of where the chi-square test actually fits in amongst all the different inferential statistics we've been learning so far. And then we're going to talk about a new kind of hypothesis testing, the goodness of fit hypothesis test. So it's going to be similar to hypothesis testing as we've been doing so far, but there's a slightly different logic behind it. So because it's a slightly different logic, there is a new null hypothesis as well as the alternative hypothesis. Then we're going to introduce the chi-square distribution and the chi-square statistic. And then we're going to talk about the conditions for a chi-square test. When can we actually do it? Okay, so where does the chi-square test belong? I know it's been a while since we've looked at this, if you're going in order with the videos, but I think it's pretty good to stop right now and sort of think, okay, where have we come from? Where are we now? So the first thing we sort of want to think about are the different independent variables that we've been able to look at. We've been able to look at independent variables, the predictor variables, right, that are either categorical or continuous. When an IV is categorical, you have groups, right, or different samples, right? When an IV is continuous, you don't have different groups. You have different levels that predict something, right? Okay, so just to give you a idea of a categorical IV, that would be something like experimental group versus the control group, or something like this. A categorical IV might be someone who gets a drug versus someone who gets the placebo, right? A group that gets the drug versus a group that gets the placebo. An example of a continuous IV might be looking at how much you study predicting your score on a test, right? So how much you study would be a continuous IV. All right. So that's one of the dimensions that we need to know. Is your IV categorical or continuous? You also need to know whether the DV is categorical or continuous. So the DV is the thing that we're interested in measuring at the end of the day. The thing that we want to know, does this thing change? This is the thing we want to predict, right? And so far, here's how we've come. At the very beginning, we looked at continuous types of tests, and those types of measures. And those were the regression, linear regression, as well as correlation. If you remember R, right? And regression was that stuff about like y equals b sub naught, b naught plus b sub 1 times x, right? So that was regression and correlation way back in the day. We also covered, we've been covering a lot of this quadrant actually, looking at t-tests and ANOVAs, right? One important thing to note that t-tests and ANOVAs are both hypothesis tests. But we so far haven't learned hypothesis testing with regression and correlation. A lot of inferential statistics in college doesn't cover hypothesis testing of regression until you get to more advanced levels of statistics. All right, so what do ANOVAs and t-tests sort of have in common? Well, they have in common that they're both categorical IVs and continuous DVs. So the IV is categorical, and you only have one IV. And your DV is continuous. So that's sort of what they have in common. What's different about them? Well, the difference is that the IV in t-tests has 2 levels, and only 2 levels. So there's only 2 groups or 2 samples. In ANOVAs, we could test for more than 2 samples. We could test for 3, 4, 5 samples, right? So the IV has greater than 2 levels. And so that's where we've been spending a lot of our time. So for the most part, continuous DVs are really important because they tell us a lot. They tell us the fine ways that we could actually be different, right? That the data could actually be different. So you're going to, it's more rare that you'll use a categorical dependent variable. That's not going to be as informative to us. But it is still possible, and that's where the chi-square is going to come in. The chi-square is going to come in right in this quadrant where we have categorical IVs, but also a categorical DV. So for instance, we might want to see something like, if you're given a particular drug or the placebo, do you feel like you're getting better? Yes or no, right? So that's a categorical DV. It's not continuous. It's not like a score that we could find a mean of, right? And so this is where the chi-square tests come in. And there's going to be 2 chi-square tests that we're going to look at. The first one we're going to cover today, and it's called goodness of fit. The next one is in the next lesson, and it's called a test of homogeneity. But they're both chi-square tests. The other way you'll see this written is chi squared. So sometimes students think, oh, what's this x squared doing here? When it has this little curvy part here, we mean chi squared, the Greek letter chi. All right. Finally, this is a test that rarely is covered in inferential statistics, but at more advanced levels of statistics, you do cover it. And this is called the logistic test. And the logistic test takes you from continuous IVs to categorical DVs. But that's a rare design used in conducting science. It's not as informative as continuous to continuous or categorical to continuous. All right, so we're going to spend our time right in here. All right, so there's a new twist on hypothesis testing. It's not totally different. It's still very, very similar, but there's a subtle difference. And today we're going to start off with the chi-square goodness of fit test. Basically, let's think about hypothesis testing in general. In general, you want to determine whether a sample is very different from expected results. That's the big idea of hypothesis testing. And the expected results come from your hypothesized population. If your sample is very different, and we usually determine that with some sort of test statistic and looking at how far it is on the test statistics distribution, right? And we look at whether it's past that alpha cutoff or the critical test statistic, right? And then we say, oh, this sample is so different than would be expected given that the null hypothesis is true, that we are going to reject the null hypothesis, right? That's usually hypothesis testing. Goodness of fit still takes that idea. We're going to look at whether a sample is very different from expected results. But the question is, how are we going to compare these two things? We're not going to compare means anymore. We're not going to look at the distance between means. Nor are we going to look at the proportion of variances. That's not what we're going to look at either. Instead, Instead, we're going to determine whether the sample's proportions for some categories, right, are very different from the hypothesized population's proportions, right? And the question will be, how do we determine very different? And here's what I mean by determine whether the sample proportions are different from the hypothesized population proportions. So here, I'm just going to draw for you sort of schematically what the hypothesized population proportions might look like. So this is just sort of the idea. So you might think of the population as being like this. And in the population, you might see a proportion of 1/3 being blue, 1/3 being red, and 1/3 being yellow. Now, already, it's hard to think about, like you could already sort of see, well, we can't get the average of blue, red, and yellow, right? Like what would be the average of that? And how would you find the variability of that, right? So already we're starting to see why you can't use t-tests or ANOVAs. If you can't find the mean or variance, you can't use those tests, right? So if this is what our hypothesized population looks like, then when we get a sample, when we get a little sample from that population, boop, right? We want to know whether our sample proportions are very different from the hypothesized proportions or not. So let's say in our sample proportion, we get mostly blue, a little bit of red, a little bit of yellow. So let's say 60% blue, 20% red, 20% yellow. Are those proportions different enough from our hypothesized proportions, right? Another sample we might get, right, is half blue and half red and no yellow, right? Is that really different from our hypothesized proportions? Another sample we might get might be only like 1/10 blue, and then 40% red, and then the other half will be yellow, right? So in something like that, we want to say, is this really different from these hypothesized population proportions? And so that's what our new goal is. How different are these proportions from these proportions? And then the question becomes, okay, how do we determine whether something is very different, right? Is this very different or just sort of different? Is this very different or just kind of different, right? How do we determine very different? That's going to be the key question here. And that's why we're going to need the chi-square statistic and the chi-square distribution. All right. So we're changing our hypotheses a little bit. Now the null hypothesis is really about proportions. And here's what we're talking about. The null hypothesis is now this. Is it that the proportions in the population are real population that we don't know? Question mark, population, right? Boop, we don't know it. Will this population be like the predicted or theorized proportions, right? And so here we're asking, is this unknown population like our known population, right? And that should sound familiar because that's sort of the fundamental basis of inferential statistics. So that's our new hypothesis, new null hypothesis, that the proportions in the populations are like the predicted, will be like the predicted population proportions. They'll be the same, right? Remember, sameness is always the hallmark of the null hypothesis. Alternatively, you want to say at least one of the proportions in the population will be different than predicted, right? So going back to our example, so if our population, our hypothesized population is something like, 1/3, 1/3, 1/3, right? Maybe what we'll find is something like, in our sample, we'll have 1/3 blue, right? But then some smaller proportion, like, 15% red, right? And then the rest being yellow, right? Now, the 1/3 should match up, right? The 1/3 matches up. But what about these other two? And so in the alternative hypothesis, at least one proportion in the population will be different from the predicted proportions, right? So it just has to be one guy that's different. All right, so just to give you an example, let's turn this problem into a null hypothesis and an alternative hypothesis. Okay, so here it says, according to early polls, candidate A was supposed to win 63% of the votes, and candidate B was supposed to win 37%. When the votes were counted, candidate A won 340 votes, while B won 166 votes. So here, just to give you that picture again, the null hypothesis population was that candidate A, I'll color A in blue, candidate A should have won 63% of the vote. And candidate B, who I'll color in red, should have won 37% of the vote, right? So what would be our null hypothesis? Well, our null hypothesis would be that our unknown population will be like this predicted, the proportions in my unknown population will have the same proportions as our predicted population, right? So here we might say something like A's votes, A's proportion of votes, of the actual real votes, should be like this. The predicted population, right? And B's proportion of votes, sorry, this is a little small, should be like predicted population, right? So it's saying A's proportion, the real proportion of votes, should be like this, and so should B's. B's should be like this, right? The other way you could say it is that the proportion of votes, the real proportion of votes, should be like the predicted proportion of votes, right? And then you could just say for every single category, for both A and B. So what would be the alternative version of this? The alternative would say at least one of the proportions, one of the categories, either A or B, one of those proportions will be different from the hypothesized proportion. And in fact, in this example, if one of them is different, the other one will be different too. Because since we only have two categories, if we make one really different, then the other one will automatically change, right? But later on, we might see examples where we have like 3 or 4 or 5 categories. And so in those cases, this will make more sense.